Hello all. In this video, we will continue these lessons on Unit 1 by discussing the Newton's laws of motion that, if I'm allowed to be philosophical, these laws shaped the fate of humanity pretty much in the modern era, okay? They found applications in everything you can imagine. So, okay, let's just a brief, I'm gonna write just a sentence for the historical part of the thing. So in the 17th century, Newton came up with his famous three laws. Okay, it's just three, guys. It's not too many laws, okay? He didn't only come up with the three laws, the three Newton's laws. He also came up with the law of gravity. He worked on optics. He came up with calculus along with Leibniz and stuff like that. So let's write that in parentheses, as well as calculus, geometric optics, gravitation, and so on. According to my opinion, he is the greatest physicist of all times, okay? You can put Einstein up there as an equal first, but I think since Newton was first and he worked without modern technology, he was at Cambridge in the 1650 something, so I think he was the greatest. So anyway, so shall we take a small detour and yeah, let's do that. Let's take a small detour and find some information about Newton. So Newton, okay. So there he is. He was born in 1643, okay. He died 1727, English polymath, active as a mathematician, physicist, astronomer, alchemist, theologian, author, and inventor. Okay, his book, this is a famous book, the Principia Mathematica, was first published in 1687, achieved the first great unification in physics and established classical mechanics. He made seminal contributions to optics. Okay, what else? Laws of motion, universal gravitation, and so on. I suggest you read about him. It's good to understand the people behind some inventions and some physics in general and discoveries and so on. I think there is a lost kind of episode in his life in that he lost lots of money in the stock market, I think. Okay, don't quote me on that. I think I remember that from reading about his life back in the day. But anyway, do your research on Newton. He was an interesting figure. Okay, back to AS-level physics. So let's jump right in and talk about the first law. Okay, first law. Okay. So objects at rest or in motion and motion is understood to be motion with constant velocity. Okay, so let's write this in parentheses. So motion with constant, let's say speed, because you don't care about direction. So objects at rest or in motion will remain at rest or in motion with the same speed and direction. Okay, unless acted upon by an external force. External, I'm sorry for my grammar, by an external force. Okay, so it's good to know these laws in writing. I mean, you should be able to write this statement down, because sometimes in past papers I've seen questions in which they ask you to write this down in some form. Okay, so it's good to memorize this. But before memorizing anything in physics in general, this is a general rule, first you need to understand it. Okay, write it down, make sure you understand it, convince yourself using examples and so on. And once you understand what the first law or any law of physics or mathematics says, then you should be able to memorize it in a way that it kind of feels internal to you. Okay, so it's gonna make your life easier. So let's see. Let's do a stupid example for the first law. Let's say that you have a car, this beautiful car, okay, that moves with some velocity v. Okay, so no forces act on it. Okay, this is an idealized example in which we assume there is no friction. Okay, so no friction with this road, no air resistance, nothing. Okay, because in the actual world there is an external force. Actually, many external forces are acting on this car, but in an idealized world, no forces are acting, so the car will happily keep moving with the same velocity forever, pretty much. Okay, so let's erase this. Okay, let's say that there is a bump. Okay, oops, let's use some color. Let's make the bump green. Okay, so if there is that bump in the street, in the road, then an external force does act on the car, right? So let's design the car again. Okay, so in this case, the external force is the normal force from this bump, right? Something like this. So since an external force acted on this car, then the car will, I don't know, it might trip. It might just go through, but you see that the velocity changes to some new velocity and then to some other new velocity and so on. So the bump here represents the external force. Okay, so in the absence of external forces, this thing will keep moving forever. And the best example is actually, let's assume you have a gun. Okay, I shouldn't be saying these things to kids. Okay, and you're in space. Okay, and you shoot a bullet in space. Okay, so you're an astronaut, you are in the International Space Station, or maybe in some I don't know, maybe you are in a spacecraft that goes to somewhere, to Mars. Okay, and let's say hello to our friend Elon Musk, who wants to go to Mars. So let's say you get outside somehow. Okay, you can do that. I mean, they do it in the International Space Station to fix things and so on. And you shoot a gun. I'm pretty sure the gun will work in outer space because there is an internal mechanism that fires the explosive part. So anyway, let's assume that it works. Okay, if you shoot that gun and you shoot the bullet in space, it will fly forever. Okay, and that's because space is empty. Okay, it's not totally empty. I think the density of, if I remember correctly, there are something like 5 protons per cubic meter in space or something like that. So nothing, pretty much. So it's empty space. So the bullet will keep traveling forever, unless it, I don't know, it hits a meteorite, another spacecraft, I don't know, it bumps into a planet, something like that. Okay, and maybe the pistol is a bad example. I mean, you can just be in outer space and throw a rock. Okay, then it will keep moving forever. And actually, let's verify the density of space. Density of space. now you have this AI summary, which sometimes is bad, but sometimes is good. So, I mean, when you Google something, they give you this summary. I cannot write on it, but yeah. So the density of space varies significantly depending on the region. In interstellar space, the average density is approximately 1 atom per cubic centimeter, though it can range from as low as 0.1 atoms per cubic centimeters to as high as 1,000 atoms per cubic centimeter in dense regions. This corresponds to a number density of about 10 to the minus 20 kilograms per cubic meters for interstellar gas. So I was wrong. It's not 5 protons. It's more like a million protons or something like that. So 1 atom per cubic centimeter. Okay, that's interesting. So let's go back and let's continue with the second law. Okay, so second law. Okay, an object's acceleration is proportional to the net force acting on it and inversely proportional to its mass. And I'm going to write in parentheses here for constant mass, okay? And what I mean by that is in cases where the mass is not constant, but it's changing. And again, the best example comes from space again. So if you have a rocket that, I don't know, that launches a spaceship or a satellite in outer space, then it has some fuel, right? So as the fuel burns, the mass of the rocket is not constant, it reduces with time, right? So Newton's laws still apply to that case, but there are some modifications. And we don't talk about that case at the AS level or the A level. So those of you who are going to go study physics at the university will learn about this. Same goes for engineers, okay? Especially engineers need it a lot. Like if you're going to be a space engineer, mechanical engineer, etc., you need to know these things. Okay. And we will come back to this second law later in these lessons when we will talk about momentum, and we'll see how it's related to momentum. Okay, so the second law tells you that the acceleration is equal to the externally applied force over the mass of the object. Okay, so if you have an object pretty much, and you have some force, sigma f, okay, this force is going to cause this object to accelerate in the same direction, okay? Notice that these are vectors, okay? So the acceleration will be in the same direction as the externally applied force and inversely proportional to the mass, okay? And these are vector quantities, okay? Let's talk about units. Okay, the units for acceleration is, we can read it off from here. Acceleration is force per mass, so newtons per kilogram, okay? But a newton is not a base unit, right? 1 newton is 1 kilogram times meters per second squared, and this is divided by kilograms. So newtons per kilogram are equivalent to meters per second squared, which you guys are all familiar with, I bet, from earlier classes and the GCE level and so on. Okay, and because I don't want you to stay puzzled about how this is related to momentum, let me just say, okay, we'll talk about this later, about this again, but notice that we can also write sigma F, total externally applied force, is equal to ma, right? But what is A? It's dv over dt, the change in velocity with respect to time, right? So we can also write this as sigma F. I'm gonna drop the vectors, okay, for simplicity. So this is equal to d mv over dt, because the derivative of a constant is 0, right? But then this quantity over here, notice that this is the momentum, okay? So this is also equivalent to dp over dt, or delta p over delta t. dp over dt is for infinitesimally small changes, which means that dt is really small, so a small period of time, whereas delta p over delta t describes an average between two events, so something like that. We will come back to this later. But when I was talking about rockets, I meant to say that, okay, if we take this, I hope I'm not confusing you. If I do, let me know in the comments and we can talk about it. So if we take this form, then sigma F is dm. So let me do it slowly. So we have dm times v over dt. What's the derivative of a product? The derivative of the first quantity times the second, plus the derivative of the second quantity times the first, right? And this is the part you are familiar with. And then we have this term here. And if the mass is constant, which I just said, I stressed this here, okay? If the mass is constant, then this derivative is zero, and you are left with what you're familiar with. But in the case of rockets, this dm over dt is not zero, right? Because the mass does change with time, because the fuel does burn. Even in a car, even in a commercial car, the mass is not constant, right? Because it burns gas. So it's the same case, okay? But this is something to think and worry about once you go study physics at the college level. So let's leave it there, okay? It's good to know these things though, it's fun, okay? Right, and even though it doesn't belong, this discussion does not belong here, I'm gonna mention it. We're gonna also talk about the third law. About the second law, you don't need to memorize how to write it down. I mean, you don't need that, because you have the formula and you can just describe the formula. But I mean, the second law is more popular because it includes a mathematical equation, okay? All right, so the third law, which again we will discuss again when we talk about momentum. The third law says when an object A exerts a force on an object B, okay, then the object B also exerts an equal and opposite force on object A. Okay, this is A. All right, so the key here is that to have a Newton's third law pair of forces, you need to have two objects, okay? So, for example, if you have a positive charge and a negative charge, okay? So, yeah, okay. Okay, so if you have a positive and a negative charge, then the positive charge is attracting the negative charge by a force F, but the negative charge is also attracting the positive charge with an equal and opposite force, right? The same happens with planet Earth, pretty much. So you see, in this case, we have two objects, okay? The first object is the positive charge and the second object is the negative charge. If we have a planet, okay, And we have that spaceship maybe that's falling onto Mars. Okay, so this planet is Mars, and this is the spaceship. Okay, or some cargo, because we are going to colonize Mars, it is claimed. So so let's say that this thing is falling onto Mars. Okay, let's go back to here. Okay, so then okay, the planet exerts a force, the weight actually, okay, the weight. So a force F, the planet is exerting this force F on the object, so it's falling. But also the object is exerting the same and opposite force on the planet, okay? I know it sounds ridiculous, but we also attract the Earth with, for example, my mass is 80 kilograms, say, so my weight is 800 newtons, say, give or take. So I'm also exerting a force of 800 newtons upwards, so I'm pulling the Earth upwards, but that's nothing because the mass of the Earth is about 6 times 10 to the 24 kilograms, so a force of 800 newtons is nothing, so it doesn't move, okay? So, yeah, so again, in this example with a falling object, we have two objects, okay? And the same force is acting on both objects, but in opposite directions, okay? Let me show you an example that is not a Newton third law pair, okay? So, okay, here is the floor. Here is, I don't know, me or someone, okay? So, how many forces is this person experiencing? The weight and the reaction force from the floor, okay? So it is tempting to say, oh, okay, the reaction force is equal, to the weight. Therefore, this is a Newton's third law pair, which is wrong, okay? So not, okay, actually, let me erase this. So this is not a Newton third law pair because the two forces act on the same object, okay? So this is key there, okay? So for Newton's third law pairs, you need two objects. All right, so let me see what I have next. Okay, we have a clean page. So I have a few examples here, so let me try to write them down before moving on. So let's do example. So how do you pronounce that? So let's okay, luge, I think, is an Olympic sport. Is that the correct pronunciation? Let's go to Brave. So luge sport. Luge is a winter sport. Okay, pronunciation. Let's see, pronunciation. Okay.
Luge.
Luge. Okay. So anyway, all right. Let's go back. By the way, as I said multiple times, I prefer to use the Brave browser because it blocks all ads and all spyware and stuff like that. And no, they don't sponsor me, okay? I hope they did, but they don't. So luge is an Olympic sport where an athlete lies on a small sledge racing down a track feet first. It sounds kind of terrifying actually as a sport. So anyway, so this is the situation. You have an incline with some angle theta, and you have, I don't know, imagine that this is the, I don't know, the sledge, something like that. And you have someone, sorry for my bad drawings. So you have someone lying on this thing, okay? And they go down, down this incline. So let's see. The question is to draw a free body diagram indicating the magnitude of these forces. Okay, and this is supposed to be on ice. I mean, this is an iced surface, okay? Okay, I had to re-record this because I realized I was making a mistake. So, okay, let's draw the free body diagram for the luge. Okay, I really like the name. Okay, let's do this. So I'm gonna draw, okay, the ramp or whatever or the track or whatever this is. Okay. Okay, so this is the angle theta. Should be a straight line. So that's okay. And let's assume that that's the athlete. Okay. So we need to draw the forces to scale pretty much. Okay. So the weight is going to be a large force. Weight is m times g. The reaction from the floor is going to be also a large force, but not as large as the weight. And there is a third force acting. Okay, we are going to assume, this is why I recorded the video again, and I will cut what I did before. So there is one more force over here, which let's call it F, little f. Okay, it is implied that it's friction, but the ice has really, really little friction, like it's almost close to zero. So this F is the reaction from the wind, okay? I mean, as the person moves in this direction, okay? F is the, sorry, not the reaction, the resistance from air, okay? And this is important, that it's the resistance from air and not the friction for what we will about to discuss. So, this is it. As far as the free body diagram goes, we drew all the forces, and F is very, very small. It's a small vector there because that force is very tiny, okay? It's not, I mean, I think they are indoors, so the air resistance is almost zero as well. So, and again, we assume that the ice has no friction, okay? Let's go to question B. The mass of the athlete affects her time for the race. Okay, I explain why the mass of the athlete has little effect on her initial acceleration. So here is the part where we have to analyze the forces, okay, or resolve the vectors, as they say. But anyway, so the motion is in this direction, parallel to the floor, okay? So we need to analyze the forces with respect to this parallel to the floor direction and the perpendicular to it, okay? So either this angle or this angle is equal to theta. Okay, I'm gonna tell you which one it is because we will continue the video, but maybe pause the video and try to think about it. Right, so let's actually talk about it now. I hope you found theta by pausing the video, but theta is, you have to think about it like this. So this weight vector is perpendicular, okay? This vector is perpendicular to to the base of the track. And okay, so this side. And then this vector is perpendicular to the floor. So the inscribed angle between these 4 lines, so this angle is equal to this angle. Okay, that's how I think about these things. So the weight has a component mg cosine theta that is perpendicular to the floor, and a component mg sine theta that is parallel to the floor. Okay, so in this direction, this one, there is no motion. The person is not moving upwards. I mean, they don't move there or anything. Therefore, meaning that r is equal to mg cosine theta, which is of no concern for this problem. So what is of concern is the second force. Okay, so sorry, the second axis, the one that is parallel to the floor. So for this axis, since the motion is in this direction, we take mg sine theta to be positive. So mg sine theta minus the friction is equal to ma. Okay, and this is the what is called the sigma f. Okay, the resultant force. The resultant force is mg sine theta minus that small not friction. I'm sorry, air resistance. Okay, so this is assumed to be larger than 0, which means that the object gets an acceleration. Okay, but if v is 0, right? Actually, let's use u, the initial speed. But if u is about, when the person starts sliding down the slope, the initial velocity is approximately 0, which means that the air resistance is also 0, because air resistance is proportional to speed. For those of you who like running, I don't need to do a lot of convincing about the air resistance being dependent on velocity, right? Because if you run really fast, you feel a larger air resistance, right, when you run outdoors. Okay, but if you run very, very slow, you don't feel any resistance because the resistance depends on speed. So if f is 0, then the initial acceleration, if f is indeed 0, because the person starts from a 0 velocity, then mg sine theta is equal to ma. So a is equal to g sine theta, independent from the mass. Independent from the mass. So the claim is indeed true. Okay. Let me see. As okay, the second question. I don't know what I wrote in my notes. I'm puzzled now. So, okay. As v increases, the velocity of the athlete, okay. As v increases, at some point, f will become almost equal to mg sine theta. Okay, in which case a will be 0 and a terminal velocity will be reached. Okay, and we can see that if we write a is equal to mg sine theta minus friction over m, then we can also write this as m times g sine theta minus f over m. So if we delete this m, we see that the acceleration is g sine theta minus f over m. So as m increases, f over m decreases. So a is larger for heavier athletes. Okay, so this part was probably confusing. So what we proved here is that the initial acceleration is independent from the mass, okay? But as v increases, at some point, the friction becomes equal to mg sine theta, in which case the acceleration goes to 0 and the athlete reaches a terminal velocity, okay? And in the third part, we try to analyze how the acceleration depends on mass, okay? And in fact, if an athlete is heavier, then this part is smaller, okay? Therefore, the acceleration is actually larger for heavier athletes just because this term that depends on wind resistance is smaller, okay? And this was a little bit of a complicated example for Newton's second law. And I think I will stop the video here because the next topic is Suvat equations, which is kind of unrelated to this kind of discussion about forces and Newton's laws and so on. So I will stop the video here, and I hope this all made sense. All right. Let me know what you think in the comments. If you run into trouble understanding, ask me. And see you in the next video, guys. And please like these videos, comment, subscribe, because it really helps with the algorithm of YouTube. I mean, they promote your videos and so on. So thank you guys for those who follow me. Means a lot. And see you in the next one.